Welcome back, guys. In this video we're going to derive the Bellman equation, and the Bellman equation is going to tell us how to be happy. So I could certainly use something like that these days. Before we start with this though, we need to introduce the idea of a state variable process x. And x is going to be just all the things that determine everything of how prices move, how our wages move. If it were a econometric equation, x would be the x's. So this is just going to be like a placeholder value that's going to describe to us how the system evolves, how information is revealed to our agents. And so we're going to define a stochastic process like this: mx dt plus vx dzt plus v hat x dz hat t. And we're going to stipulate that dzt and dz hat t are independent. So the covariance of dz and dz hat is 0. What this means is that if dz hat, let's write this as the v's, not the dz's. So we're going to say that v of x and v hat of x, the covariance is 0. So if v hat of x is greater than 0, we're stipulating that the market is incomplete. Why? So we know that you can hedge away risk of these DZs by diversifying your portfolio. What we're saying is that this V hat is uncorrelated with this diversifiable risk DZ. So if V hat is greater than 0, then there's something in the market that you can't buy, some risk. So for example, say that nobody sells meteor insurance. So if a meteor strikes the earth, you're screwed. There's nothing you can do, and there's nothing you can buy to help you in that situation. So that's like what this would represent. This allows us to have incomplete markets. But so this is just a technical side note. What we're interested in really is this Bellman equation. So we have this process x. And so how do we maximize our happiness forever? We're going to make an equation j. And this equation is going to depend on our wealth. It's going to depend on the information and the time. And we're going to maximize our consumption and our portfolio allocation such that our expected future utility of consumption forever, so 0 to t, that's our whole life. We're going to discount. We're going to have a discount factor, so we care more about the future than we do about, we care less about the future than we do about today. We're going to gain utility from consumption, and then we're also going to gain some utility from leaving things behind to our kids, right? So t minus t, we're going to go backwards, and that's going to be u bar w of big T. So this one goes backwards. It gets stronger and stronger as time goes to the end. And all of this is conditional on w, x, and t. Okay, so how do you solve a Bellman equation? I think for me, what helped me to understand it was to look at the discrete time formulation. So let's just take a quick detour, and this isn't going to help us to solve this, but it's going to help us gain an intuition of what we're doing. Suppose that we were not in continuous time. Suppose that we were in discrete time, and so instead of using integrals, which we don't like, we use these sigmas, which we don't really mind. We would want to find, again, the expected value of the sum from t equals 0 to big T of rho, which will be our discount factor, less than 1, t, and the utility of ct. And then plus again, we can do the same thing, rho t minus t of u bar wt, conditional on w, x, and t. So this is the forever problem. With C0 known. We need to know where we start, otherwise we can never solve the problem. Which actually means there's a little tiny bit of this problem that we can solve. Let's take this and see how it looks tomorrow. So if we consider the vt plus 1 problem, we would be the max of ct and pi t still. And now we're just going to start our index, it's kind of a derpy sigma, at t equals 1. And everything else is the same. So really, this problem can be decomposed into two problems. So we'll call this the tomorrow problem. It can be decomposed into the today problem and the tomorrow problem. And they're almost the same thing. And so if we write it that way, you could say, well, we maximize today using that CT0 that we're given. The utility of C0, and then we add to that everything else. We add to that the tomorrow problem, the VT plus 1, conditional on our WXT. And so this is going to give us the intuition. This is now a solvable problem. We've gone from this thing here, which was this forever problem that's quite daunting, and we've turned it into a very simple problem with just two parts that we know how to solve in theory. So we can do the same thing in continuous time. What we'll do is we'll take our forever problem and we're going to cut off a very, very small part of it that we're going to call delta t. So we're going to maximize first this little bit that we know, and we're going to have that little bit for delta t time, so that's how much utility we get out of that. Plus, we need to discount now the tomorrow problem because delta t time has passed when we begin solving this, so we need to additionally discount that little delta t, and then we put the rest of it, the rest of the problem, which is going to be delta t when we start to t, and then e to the minus delta times s minus delta t, utility of cs plus e to the minus delta t minus t, I guess t minus s, sorry, kind of bad, wt, and then imagine that I write ds. There's a ds here and a ds here. And there was also a ds here, I apologize, and a ds here. And then the conditioning information. Okay, so now we have these two bits. And we can actually solve some of this. But first we need to rearrange. What we want to do is we need to pick the smallest possible delta t, a teeny tiny delta t. So what we want to do eventually is to take the limit as delta t goes to 0 of this whole equation. But there's a few things we can do to make it a little more convenient first, because we really want this part to go away or to become something we can do something with. So let's take this e and this delta t over to this side. So we'll multiply everything by e to the minus delta t, because that's a minus. So we get e delta delta t divided by delta t j wxt is equal to the max of ct and pi t. Now we multiplied by e to the delta delta t, u of ct, and then we divided by 1 over delta t, and then here we can just write the expectation of our tomorrow problem, or now it's like our next second problem, so it's going to be j of wt plus delta t, xt plus delta t, and t plus delta t. And I've been very lazy with my subscripts and things. I apologize, but this is all t's. There should be t's, you know, here and here. Anywhere else? I don't know. But yeah, you know, I'm gonna drop the conditioning information. You know, I do apologize about that, but it's past midnight. You gotta cut me some slack here. Okay, so one last thing is to make this go away when we take a limit. If we subtract j t plus delta t blah 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 minus a j wt xt t, we're just going to end up with dt. We're going to end up with just that tiny little variation, which is actually the definition of the drift term. 1 over delta t times this j t plus delta t minus j wt xt t. That's the definition of the drift. So let's actually write this out. So we're going to subtract off one thing from the left-hand side here. J wt xt is equal to max ct pi t e delta delta t u ct plus 1 over pi delta t expected value of j wt plus delta t x t plus delta t t plus delta t minus j w x t, and there's t's here, t. Okay, so we are now ready. We can take the limit of both sides. We will take the limit of this as delta t goes to 0, and the limit of this as delta t goes to 0. So here we have to use L'Hopital's law, L'Hopital's rule. So derivative of the top and bottom, we just get delta. I guess we'll get delta e delta delta t minus 0, because the derivative of that with respect to delta t is 0 over 1. And then we take the limit, and this goes to 1, so we're left with just delta. So we get delta j wt xt t is equal to the max ct pi t. The limit of e delta t, that will just go to 1, so we get u ct plus, now this whole thing, like we said, that we define the limit as delta t goes to 0 of this thing, 1 over delta t expected value blah blah blah, is defined as being equal to the drift term of this function j. So I'm just going to call that mu of j, but just to make it compact, because this is our Bellman equation. So in the next video, we're going to actually compute this mu of j, which is a huge messy equation coming from Ito's lemma. So I'll see you there.